Hello, it's Professor Guldan again with another video. This is the video answering the question, what effect does temperature have on spontaneity? So in the first video, we talked about free energy changes and how those are connected to enthalpy and entropy and total entropy, and how it's a much faster, more efficient way of finding whether or not a reaction or process is spontaneous, at least in a thermodynamic sense. So now we want to think about what happens if we take into account that not everything happens at 25 degrees Celsius. So if we think about our equation, and I'm going to use this fancy pen to remind us. So normally I'd write this on the board, but I'm going to try this. So delta G, right, equals delta H minus T times delta S. So we have several cases that are independent of temperature. For example, if our enthalpy is positive, so we have an endothermic reaction, and delta S, or our entropy change, is negative, we have always going to be positive, right? Because this is positive, and a negative times a negative T will always give us a positive. So we'll always have a positive delta G, and it'll never be spontaneous, no matter what the temperature is. We also have things that are always spontaneous. If our enthalpy change is negative and our entropy change is positive, we'll always have negative minus a negative at all temperatures. It'll always be negative, and those reactions will always be spontaneous. Note that delta H is generally a larger contribution to delta G, usually in kilojoules per mole, and delta S is usually a smaller contribution in joules per Kelvin, but it depends on the temperature, this term. So we also have temperature-dependent cases. These come about when we have reactions that have either both negative entropy and enthalpy changes or both positive. So if they are both negative, we anticipate that the reaction will be spontaneous below a certain temperature. And if they are both positive, we will anticipate that the reaction will be spontaneous above a certain temperature. So here's a table from your book that summarizes all of this, and I'll take this time in the video to remind you that you should be reading your book probably more than you have been earlier in the semester. So reading it before you view the video, and then again after you view the video, keeping track of questions as we go along, writing those questions onto the chat on Sakai so we can discuss them on the chat feature, and also bringing those questions to the Google Meet office hours. So on this table, we have our always negative down here, always spontaneous, oops, sorry about that, and always not spontaneous. And other things depend on temperature. So if they're both negative, we expect them to be spontaneous at lower temperatures. And if we have both positive entropy and enthalpy changes, we expect them to be spontaneous at higher temperatures. Again, we can always just use the equation that defines delta G. Delta G equals delta H minus T times delta S to figure this out. Here's also a picture version of the same thing, right? So we can get this idea of what's going on. So we still have our always non-spontaneous, always spontaneous kinds of reactions. So what happens to delta G as a function of increasing temperature? So if we increase the temperature for non-spontaneous things, they stay non-spontaneous. And if we increase the temperature for spontaneous things, they stay spontaneous. There are these two in the middle, right? The ones that depend on temperature. So spontaneous at low temperatures become non-spontaneous at some particular temperatures. Spontaneous at higher temperatures are non-spontaneous until you heat them up to a high enough temperature and they become spontaneous. So we want to think about what temperature does this reaction become spontaneous. We're going to go back to our definition of free energy changes, right? So the free energy change depends on both enthalpy and entropy and temperature. So if we think about when this switches, well, it switches when delta G is equal to 0. So if we simply set delta G equal to 0, we can then find that the temperature at which that happens is just the ratio of the enthalpy change over the entropy change. Right? So finding that temperature where something becomes either non-spontaneous or spontaneous is just T equals delta H divided by delta S. Let's do one quick example so we can walk through how this works. So in this example, we have the following reaction is non-spontaneous at low temperatures. So we expect it to have a positive entropy and a positive enthalpy change. And the question says, determine the temperature range that the reaction is expected to be spontaneous. Okay, so from our previous slide, we'll use our fancy pen again. The temperature at which that happens, right, is just equal to the ratio of the enthalpy change, delta H, divided by delta S. So what we need to do is determine delta H and delta S. And here's where I miss you guys, because here's where I would ask, how do I find delta H? And generally, 3 or 4 hands will go up, or on a good day, if you're all mumbling along with me, you would say, oh, we can do that products minus reactants thing, right? So delta H naught of a reaction is just the enthalpy of formation of products minus the enthalpies of formation of reactants, all times their stoichiometric coefficients. So if we do that for delta H, we will find that delta H is a positive 58.07 kilojoules. Similarly, we could do the same thing for delta S. Find the standard molar entropies of our reactants minus the products and find delta S. But I wanted to show you another way we could do this. If we didn't have those pieces of information available, if we didn't have all the entropies we needed, we could find delta G and then get the entropy change. So let's go through that process. So we can find the delta G of the reaction in a similar way that we found the delta H of the reaction, right? The standard formation free energies of the products minus reactants. So if we find those values, we need to look those up in a table, either the paper tables I gave you or in the back of the book, the appendix, or your ebook appendix. We can find that delta G of this reaction is 8.83 kilojoules. So now we have delta G and we have a value for delta H. Since delta G equals delta H minus T delta S, we can substitute those values in. 8.83 kilojoules is 58.07 kilojoules minus the temperature, in this case, room temperature, 298 times delta S. So at room temperature, delta S is 0.165 kilojoules per Kelvin. And our temperature, using our handy formula here, temperature is just then the ratio of delta H over delta S. So we get a temperature of 352 Kelvin. So note that the question asks, determine the temperature range. Oops, sorry about that. So what we really want to think about is this reaction is spontaneous above that temperature. Below that temperature, we get a positive delta G. For example, at 298 Kelvin, we got a positive delta G, positive 8.83, so it's non-spontaneous at room temperature, and it's not spontaneous any temperature below 352. It's a 0 at 352 Kelvin and should be negative delta G anything above that temperature. Okay, so there is more practice on these concepts in Activity 20. So now that you've viewed this video, you should go to Sakai, look at Activity 20, work through those problems, bring questions to the Google Meet office hours, and also to our online virtual chat room in Sakai. That's it for now. Bye.